Okay, so let us start now. So the previous day we were discussing about parameter estimation, and we were in particular yesterday discussing about parameter estimation. Sorry. In the context of maximum likelihood. Okay, maximum likelihood estimation. So this is one of the possible strategies, and this is arguably the most popular one. Of course, then you can say, okay, I have done fitting of parameters like minimizing chi-square, etc. But chi-square is like equivalent to maximizing the likelihood. For example, in the particular case where you assume that the likelihood is Gaussian, then maximizing this Gaussian likelihood is completely equivalent to minimizing the chi-square. So most of the time, when we are doing parameter estimation, we are actually maximizing likelihood in a way or the other. Okay, so but now the thing is that okay, you have estimated your parameter, so you have your estimator of your parameter theta. Your estimator is theta hat. So the question here is now what is the error of this estimation? Okay, and this is what we are addressing today. So again, I don't know, suppose, so you have some observations, and these observations, you have assumed some PDF for it. So you have some PDF for that, and this PDF depends on some parameter theta. Then what we want is we would like to report something like this. So we want to have something like, I don't know, let me just put a random number here. So plus, minus, I don't know, whatever, 0.41, okay? This is a desirable outcome of our analysis, right? We have uncertainty on the parameters we are inferring. What does actually mean this thing? This plus minus whatever. It means actually that so if the experiment were repeated many times, so this would be like the standard deviation. That would be like the standard deviation of the distribution of our estimator, right? Upon repeating the experiment. Okay? That is more or less the interpretation you will have. Imagine you have another data set, and if you have another data set, of course, you will have another estimator, right? Because the data set is random. And then if you take a set of measurements, or a set of experiments like this, you may be able to report something like this. So there are some possibilities here. To estimate this error, right? This uncertainty in the parameters. The very first possibility, the simplest possibility, is an analytical one. So analytical estimates. And this is the case if the variance of our estimator is analytical, right? So I am just referring to this object, as you know. So I'm just writing the variance of my estimator. So this is just expectation value of the square of the estimator minus the square of the expectation value of the estimator, or the square of the mean. A very simple example, which is actually interesting, is like you have, for example, the radiative decays of a particle. Okay, so what happens here, imagine that you have collected your data. What is data here? Data is just a collection of times where the particle decay. Okay. And then you propose a distribution, you propose a likelihood, right? You propose a likelihood, which in this case is, I mean, in physics, you know, I mean, this is just obviously the exponential distribution. This is a distribution. This distribution is the one that describes the decay, random decays of a particle. E to the minus t, let me put it in this form, okay? There are some people putting, instead of 1 over tau, they put a constant there, like beta. I think yesterday I put beta, but okay, it's the same. Right, so in this case, if you plug this formula and then this formula here, and then you compute this, it is a two-line computation that leads you to the variance of my estimator for tau, and the estimator for tau, by the way, is the mean. Is going to be the mean of this. So the tau hat is going to be the mean of all this decay. It is because the first moment of this distribution is just the mean. Oh, sorry, the maximum likelihood. The maximum likelihood of this parameter is just the mean. And then you see that what you get is just this result, where n is the number of measurements from 1 to n. Which you can, of course, replace by your estimator itself divided by n. So this is just the mean, okay? And by the way, I think that yesterday we obtained a very similar result for the case of the Gaussian, but it is exactly the same thing. So you have the same behavior of the variance. Scaling has 1 over n. As you increase the data, the length of the data, you get a reduced variance, and this is something known for many distributions, for the Gaussian, and also in this case for the exponential, right? So this is just a typical example where you can say, okay, I can really do this in a back of the envelope computation, and then you get the uncertainty of your estimator is just this one, or the square root of this one. So you would report something like the value of this plus minus the square root of this variance, okay? Fine. However, as you may already notice, I mean, this is a very simple situation and not very typical. So there is a very powerful way. I think that this was raised yesterday, which is Monte Carlo method. So what is the Monte Carlo method I'm talking about? So it is referring to the bootstrap method, or bootstrapping, I don't know. So the idea here is, first of all, you have the following. So imagine you have your data, your real data. So this is the real data. With the real data, so this is like the step one, right? You are able to find your optimum parameter by, I don't know, maximizing the likelihood of the data. Let me call this theta MLE real. Right? Second step, you go and then since you have the likelihood, the shape of the likelihood, then you can actually take this as a true parameter. You pretend this is a true parameter, and with this you can generate a large number of data sets. They have to be identical to the real one, okay? To the real one, but you generate, I don't know, thousands, hundreds of thousands of data sets, depending on the data. If it is very complicated, you may need more samples for more synthetic data like this. So let me call this. Let me call this procedure. You have data. Let me call this data simulated. I mean, where S is going from 1 to number of NS. I don't know. This can be order of 10 to the 5. I don't know. So for each of these data S, you may follow exactly the same procedure as before. This will give you an estimator by maximizing the likelihood corresponding to this data set, which I labeled with S, right? And then what you do is that you have this collection, right, of estimators. You have this collection of estimators, of NS estimator, and make a histogram. So you can do a histogram of your MLE, right? Whatever. And this is actually this defines the distribution of your estimator. And since it defines the distribution of your estimator, you can, out of this distribution, let me call this distribution bootstrap distribution. You can actually compute the mean, and you can compute the variance of this distribution. And that will give you what you report here, like, let me call it, or I don't know, this. And then with this, you can just, I don't know, take the square root, etc. But you have the, it will allow you to compute the delta that you are were actually interested in. And this is the way to go, and this is very powerful because it is something that does not assume any distribution for the estimator itself. Okay? Of course, you need to assume a distribution for the data. You need to assume some likelihood, but it is not guaranteed that this distribution is Gaussian always, unless the data is very large, etc. So this is something that people, experimentalists and data analysts, they actually, this is what the proper thing to go, the proper way to go if you want to not to avoid biases about assumptions on this distribution, on the distribution of this estimator, okay? And actually, I've prepared some, so there are some notebooks today that I can show. Let me, yeah?
I have a question about this, Brian.
Yeah.
So the simulated data, to say it somehow, it is done, I guess, with theory, but sometimes theory will not agree with the real data. So
with theory,
well, So like how important is it that the simulation is like faithful or whatever?
Yeah, okay. So what I can say is the following. You can have you have your data, your real data, and your real data will allow you to compute some like a maximum likelihood estimate of your parameter. It will maybe that your real data, that you are unlucky and that your real data is actually not representative of the true distribution, of the true underlying distribution. If this is the case, then this will be a poor estimation of the true parameter theta. If it is a poor estimation, then all the rest, this procedure of generating synthetic data sets will be completely biased. If this is biased because your data is not representative, because you have a statistical flux or whatever, then of course you will produce a series of data sets which will inherit this bias.
Yes, but my question is like when you do the Monte Carlo and the mean value you get for the estimator is very different from the real value, then I guess that how do you interpret the variance you get? Because can you assign it to the real value or?
Okay, let me see if I understand the question. Your question is not referred to this.
So
part.
when you say that you do the Monte Carlo, you get a mean value of the estimator.
This thing.
Yes, the mean of this can be in general.
Mean value of the estimator. So you're talking about this.
Yes. What happens if it's very different from the measured value?
From the
real.
From this one.
Yes, exactly.
It shouldn't be. If you are producing a large number of synthetic data sets, it shouldn't be, because I mean you are generating something from this, so it in general it will be close to.
Okay, I think I understand. Okay, thank
you. The procedure, when you do the procedure, you realize that so imagine that you have, of course, if you generate 10 data sets, which is a very small number, then the mean will be different in general. So you have some difference, but as you increase the number of data sets, this will be closer and closer to the real thing, to the real estimator. Okay, so let us see an example that maybe complements the answer to this question. What I wanted to do, I wanted to stop sharing. I wanted to share the computer, desktop. Okay. So you see my like this notebook? Do you see it?
Yes, we can see, yes.
Do you see? So do you see this example bootstrap thing?
No, we see a Zoom window.
Zoom. Oh, why then? Okay. So let me see how can I do this. Because I wanted to share. Let me try again. Share the screen, desktop, desktop too. Yeah, okay. Okay, do you see it now?
Yes.
Yes.
Is it big enough? Because I can zoom in the text.
It is big enough. Yeah.
Okay, right. So then, okay, what I'm doing here is just to put an example of this bootstrap thing. Okay, so this is just a Python notebook. I hope you are familiarized, most of you, with that. And then I'm just I'm just generating my real data. Okay, so I'm just taking I'm pretending I have this data. What is this data about? This data is pretending to be 100 times collected from a decay of a particle. And this I have just generated by a true value of the parameter, which I put to 1, and I just sample the exponential distribution 100 times, okay? So whatever, I mean, God gave me this data, okay? Then I know, because this is analytical, that the mean, that the maximum likelihood estimate of tau is given by the mean of the data. So I have the mean here, and it turns out to be 0.90, almost 95, which is actually close to 1. And then I will implement this bootstrap, and then for implementing the bootstrap, I have, let me just execute this. For implementing the bootstrap, I have I have chosen a number of experiments to be, I don't know, 10,000, let's say, but I will study the dependence on the number of pseudo experiments in a moment. And for each of these experiments, I generate some data, the same size, I mean, so yeah, identical to the real one, having as a true parameter the maximum likelihood estimate coming from the real data. Do you understand this? Then I just, what I just do is that, okay, I will, for each of these data sets, I am computing the maximum likelihood estimate. And this is going to be just the mean of that particular synthetic data set. So I will have a collection of 10,000 maximum likelihood estimates for tau. And these guys are plotted here, okay? And then the only thing I need to do is to say, okay, I have this distribution. I'm just taking the standard deviation of this distribution with this function, so numpy std. And when I use this, I get what you see here, this 0.95%. I am comparing this, so how good it is. So let me compare it with the analytical results, because the analytical result, I solved it for you some minutes ago, and it is just the standard deviation is just the square root of the variance, and the analytical variance was this tau squared divided by n. And when I do this, is very similar, right? So what I obtained with 10,000 pseudo experiments was very similar to the standard deviation I obtained. It was very similar to the analytical one. So it is a good thing. So now what I wanted to show you finally is just what if I didn't choose 10,000, but I chose something else, like 10 experiments or 100 experiments. I mean, very few number of experiments in this technique. You typically go to the thousands or hundreds of thousands, etc. So what I'm doing here is to repeat the same thing for 10 pseudo experiments or hundreds of experiments, etc. And I am computing for each, in each case, I am computing the relative error from, so I'm just relative error of the standard deviation I get with respect to the analytical one. So I divide it by the analytical one. So this is just in percent if you want. And this is what I get, okay? This plot here is the relative error of the standard deviation with respect to the correct or the analytical result. And then you see that that as you increase in the number of experiments, of pseudo experiments of pseudo data, you get a more and more precise or correct value of the variance of my estimate. So this is the example I was bringing to you. Is there any question here?
I have a question.
Yeah.
Go ahead.
Yeah, I'll go first. How, because here you're comparing like the fake data, like the Monte Carlo method with the analytical, but how would you generate the fake data if you don't know like the distribution that the original data follows, like if you don't have the analytical expression?
I'm sorry, I didn't understand the question. How do I generate the what?
Right, so if you, like, how do you generate the fake data if you don't have the analytical expression for how the random variable behaves in the first place?
Oof, I still don't understand what you wanted to say. So how do I generate this data? So you're wondering about the data the real data generation? I mean, the real data in quotation.
No, I'm saying in the case that you don't know the distribution that your random variable follows, how would you generate the fake Monte Carlo data?
No, I mean, I am assuming I something for the distribution of my observable.
Yes, I know. But like, if you're assuming that you can always compute the analytical estimate, why do you need the Monte Carlo?
No, no, sorry.
And if you,
this is not true. I mean, you can have a very complicated likelihood. This is a very simple one. And if I were a Gaussian, were also simple, but imagine that you're now dealing with a model having not one parameter to fit, but having, I don't know, 1,000 parameters to fit. It is intractable, this. I mean, it is not a tractable problem. It is something that you can't do analytically. Okay, so this is just one of the few cases in real life that you may have access to analytical estimates. Did I answer the question?
yeah.
Okay. Androniki?
Yeah, so the distribution of the histogram, is it Gaussian because of the central limit theory?
So let us try the following. So with 50, it's obviously not Gaussian, right?
Yes, right.
Yeah. So as you increase, then you will get more symmetric distribution. Yes.
Mm-hmm.
Yeah, indeed. It is just that, okay, I mean, if imagine that the real data is very, the size of the data is very small, then probably this estimator of the real data is biased.
Oh, okay.
But then indeed you can generate an almost infinite amount of pseudo experiments out of a biased estimator, right? And it will be symmetric. Yes.
Mm-hmm.
Yeah. Okay. Any other question? Sorry, I don't know if I answered.
Is there a way to understand if our data is biased, if the maximum likelihood estimator is a good estimation of what's under the data?
Can your question can it be translated to the question of, is there a way to compute the bias of my estimator? Is this question equivalent to your question?
Yes.
Yeah. So the bias of an estimator. So by definition of the bias, you would need to know a priori the true value. No, because bias is like the expected value of the estimator minus the true value. So if you see the definition, then the answer is probably no. However, what is happening, and now I am referring, Aurelio, to this typical thing of machine learning that you do training and test, and then when you when you complexify the model, I mean, if the model becomes more and more complex, you will be able to fit the data better and better. However, at some point, the test data set is not going to be representative because you will have overfitting, right? Having overfitting, so if your model is doing overfitting, that means that you will have a large variance and a low bias for the training data. So the other side of that behavior, where your model is too simplistic, is too simple for the data, then you will have a very small variance, but a very high bias. So my answer to your question would be, if I make sure that I am not doing overfitting nor underfitting, I mean, let me rephrase. If I am sure I am not doing, if I make sure by some algorithm that I am not doing underfitting, then I am probably ensuring that my bias is small, because I am getting a model which is complex enough in order to describe the data. However, I also need to ensure that I don't do overfitting. But regarding the bias, as long as I know that I am not underfitting my data. So what does it mean in a context? So imagine that you have a complicated data set, and that tau here is, which is the mean of the distribution, is given by a too simple model, depending on other parameters. And it turns out that if it is a too simple model, I don't describe well the data. This can happen. And in that case, you will have a large bias. Yes.
Okay.
Yeah, but
Thank you.
indeed,
Before you say
it is a question that I mean, whose answer now I'm able to give, but like in a context a bit out of the scope of this point. But because if you, going back to my comment, I mean, if you go back to the definition of the bias, then you a priori you may need the true value. So that definition is probably a little bit useless, no?
thank you.
Sorry?
No, I just say thank you.
Okay, no, thanks to you. It was a very good question. Okay, any other question here? Okay, so let us go back to what? Let us go back to the notebook, to the notes. Okay. Okay, so I was talking about the bootstrap, and then I can talk about. Okay, it's probably worth doing it. I can talk about a third method. A third method, like the graphical method. And in the graphical method, so the idea of the graphical method here, so no, let me, before the graphical method, I will talk about the other thing. I will talk about another method called making use of this bound called Rao-Kramer-Frechet bound. This RCF. So, I mean, why this is useful? It is useful because in many practical situations, this Monte Carlo method is costly in general. Of course, I just show you a very simple bootstrap, but if you have a lot of parameters, this can be very costly. So it is useful to have an alternative, and the alternative is the following. So this RCF bound is a bound on the variance of my estimator. So let me write it like this. So it is computed, or it can be expressed, it is computed in practice in the following form. -1 over log of the likelihood divided by theta squared. So the second derivative of the likelihood with respect to the parameter evaluated at the value of the estimator. Okay, so here we can just put an example. So imagine that I have a likelihood which is let's say which is a Gaussian. So I am just computing the log likelihood, which is just the sum of the log of some Gaussians given by some data theta, and then imagine I just know what is the variance of this Gaussian, and every point has the same variance equal to 1. So when I compute this, then if I take the log of that Gaussian, if I take the log of that Gaussian, then I first of all have the log of pxi theta. This is just xi minus theta, right? And so sorry, with respect to theta, which means that the second derivative of for every point, it is just the derivative is just -1. So the denominator of this bound here, in this simple case, it is -n, because for every point it is the same. Which means that this bound, what it's telling me is that you have 1 over n. So this is like the RCF bound on the variance of my estimator, and here again you see the trend, no? How it is going to 1 over n the variance, no? This is like another way of getting it. Okay. Any questions here?
One question.
Yeah.
So if we have a multivariate distribution, can we calculate the bound for the covariance matrix in that way?
Say it again, sorry. If we have what?
A multivariate distribution. So we can do the same for the covariance matrix, or? like taking derivatives for theta I and theta j?
I think, if I remember correctly, I think that there is a multivariate formulation of the Rao-Kramer bound,
Oh, okay.
which is a generalization of this expression.
Mm-hmm.
But it is like the typical thing. So it is a generalization which is in a paper. It doesn't mean that it is a standard procedure. I cannot guarantee that what I have seen, that I can pass you the reference later, is a standard like a procedure for everyone. But at least I know this has been formally generalized to the multivariate case. Yes. Yeah. So, but you don't. What I remember is that you don't use this like repeatedly for all the parameters, because of course you need to take into account the correlations between the parameters. No, so the off-diagonal elements, etc. So this is typically here you will have typically the derivative with respect to right, this subsection, right?
Thanks.
But yeah, there is a generalization for that. Okay. Fine. So this is the Rao-Kramer one, and it's very useful in order to at least to expect to know what you can expect. So let us then go to the graphical method that I was trying to introduce before. And the graphical method is very well, it's very visual, of course. Or it relies on the following theme. So you consider the case of one estimator. So you have one parameter in your model. And then what you do is to say, okay, I will have my, let's say, my estimator coming from maximum likelihood. And I will expand the likelihood or the log likelihood around this value. So if I expand it like a Taylor expansion, so then I will get the log of L as a function of theta is, okay, the log of L evaluated at my estimator. I'm just writing the first three terms. Sorry, log of L with respect to theta evaluated in. Okay, I'm just let me just save notation here. This thing theta hat is just the maximum likelihood estimate times theta minus theta hat plus 1/2 of the second derivative, and I will stop here. So the idea is that if your estimator is the maximum likelihood estimate, then this term is 0. This goes away because you have maximized your likelihood, right? And then what you do is to use the Rao-Kramer bound in order to re-express this part. And if I use this expression, I can write the following: log of L of theta is log of L. Let me call it L max, because if I evaluate L in the maximum likelihood estimate, I will maximize the likelihood. So this is log of L max minus this quadratic term, right? Divided by 2 sigma, the Rao-Kramer bound. So I'm substituting this, the bound, I am assuming this is an equality. And then I get this. So once I have this expression, then I can evaluate this expression in theta hat plus minus variance, standard deviation of theta hat. So substituting here, I get log L max, so this is a constant, minus 1/2, isn't it? So if I substitute this thing here, then I will have cancellation of this goes away, and then I will have in the numerator this theta, this sigma, which will cancel with the sigma. So I have this result. The interpretation of this is that a change in theta of 1 standard deviation from, away from its maximum likelihood estimate, of course, will produce a decrease in log likelihood by 1/2. Okay. So this is the thing, and it is very interesting how this works actually. So let me again go to another notebook. Is there any questions before going to the notebook about the method? Okay. Yes, I see something. I hear something. No.
I guess that this method is valid when like third order terms and so on are not very relevant when you go away of the likelihood by this factor of minus 1/2, but
yeah,
I guess that it's risky to use. Maybe it can fail easily, or so. When do you use this method and so on?
Yeah, indeed. You are just neglecting that the third order terms. And what I can say is that if the distribution here is a distribution, sorry, let me just write something here. So let me see an example, and then I answer the question if you don't know. I think it is better with the numerical example. So 1 second, I share screen here, desktop 2. What graphical uncertainty? That was before. Exponential. Okay. So here I'm just doing this thing with exactly the same data generation. So I am using exactly the same data as before. So this data, it is identical here. And what I'm just using is, okay, I first of all repeat what is the maximum likelihood estimate. And I have just this is just a function of my likelihood, defining my likelihood. So this is a log likelihood when the likelihood is an exponential. Right, so the log max, the log of L max is just this function evaluated in the maximum likelihood. And then I plot. What do I plot? I plot for a given tau in a given range. I plot the log likelihood, and this is the blue curve here. Do you see it, or you don't see it? Now you see it.
Yes, we can see it. We can see it.
But before you were not able to see it.
No, we have been seeing it the whole time.
Ah, okay. Okay, so then this red line is just this log max minus 1/2. So note something, I have zoomed in a lot this plot. So this is a very zoomed in plot, but if I increase this plot, so let me try to, let me see if this works. Okay, so imagine I don't zoom in the plot. So here you will see the non-Gaussianity. So in general, this likelihood, sorry, the likelihood of this shape is not Gaussian, right? However, if I zoom in the interesting region, it is Gaussian. I mean, it is very symmetrical. So for example, if I consider instead of this, let me take an even more range for X. So if I go from, I don't know, from 0, 1 to 10 or so. Oh, okay. No, not. What did I do? I wanted to put 10. Sorry. So this is the point I wanted to make. So the distribution is quite non-Gaussian. But now you are focusing on the expansion of this likelihood around the mean. So I'm just focusing on this very narrow range here. And then what you see is that this is symmetrical, right? And that means that I mean, this is really this is like giving a more accurate result. Huh? The whole thing about this method is the fact. I'm sorry, by the way, let me just finish the example here when I just compute what is this intersection and this intersection here. And when I compute this and I subtract this value minus this value, that should be 2 standard deviations, right? Because it is just plus minus 1 standard deviation. So I divide this by 2, and then I get this value, which was very similar to what I obtained with the bootstrap. With the bootstrap here. And was very similar to the true value here. So in this case, this is a method that is working nicely. Okay. Of course, I mean the thing here is that I have substituted also the Rao-Kramer bound, the equality, and not only and not make an inequality here. And this is implying that actually this is a Gaussian thing. So this is implying that the distribution is Gaussian, right? So in cases where this is not the case, of course, this method is not that good. It is better to do bootstrap, of course. I am assuming some sort of Gaussianity here, while in the bootstrap method, you don't assume the Gaussianity. Is it more or less answering the question?
Yes, thank you.
Okay. So let me
one question
here or
for that one.
Yeah.
So the way that we report the uncertainty on the parameter doesn't imply Gaussianity too in general, not only at this example.
Yeah, right. So no, and you will see in some minutes. I mean, this is I'm just now going to the case where, in general, this doesn't have to be Gaussian, and how do you do it?
Okay.
Okay, But what I can say in any case is that these methods are not limited to the Gaussian. In particular, the bootstrap method is not limited to have a Gaussian distribution of the estimator. Right, and then in general you can, I mean, by seeing that distribution here, which may be non-Gaussian, imagine that you have a non-Gaussian distribution here, then you can report what is the containment to the left and to the right.
Yeah, yes, but not as plus minus the standard deviation.
Yeah, exactly.
Okay, okay.
Yes, exactly.
This is what, yeah. Okay.
So,
if I
yeah.
can, I also have a question.
Yeah.
To prove this this relation with the -1/2, we use this Rao-Kramer formula.
Yeah.
We assume that it's exactly whole. So I was wondering if we have the likelihood, because here you are computing it, why don't we just calculate that? I mean, exactly doing the derivatives, and we use this method.
Wait a second. So you are. Let me try to understand your question. So you have the likelihood. You can compute the second derivative of the likelihood.
Yeah.
Yes. And what do you do?
And they can find that Rao-Kramer bound, no?
You can find the Rao-Kramer bound, yes.
Yeah,
but
exactly. So I was wondering why should you use the graphical method, which assumes the Rao-Kramer validity to be an inequality when I can directly compute it, like analytically? I mean, which case could be that I have to use this graphical method and I can't use the Rao-Kramer one?
I mean, the Rao-Kramer bound gives you. Let me see. I am confused. The Rao-Kramer bound here gives you a bound. It is not giving you the uncertainty, right? It is just a bound on the uncertainty.
But okay, but to prove this formula, we have assumed that this bound is an equality when you remove the second derivatives, or did I miss something?
I am not assuming that the standard deviation of my estimator is given by the Rao-Kramer bound. I am just replacing the second derivative by the Rao-Kramer bound, but it doesn't. I think it is not. It doesn't imply that you will have the same answer if you were just stopping there and that's it, right? But in any case, imagine that you have your likelihood.
Mm-hmm.
So once you have your likelihood, you can compute the second derivative and do this and apply this bound. But I am not sure that you can actually do this always, right? So this is just this can also be I don't know, complicated to compute sometimes. And here instead, what I have used is the Rao-Kramer bound, but without actually computing it. So I in this method I don't compute the second derivative, isn't it?
Okay.
So I am avoiding the computation of the second derivative, which may be a complicated step, by assuming this is Rao-Kramer bound, and then I just get rid of this factor, and it happens to cancel this this sigma. Yeah, so that is the complementary. So that is why complementary, because you don't need in this method, graphical method, to estimate the second derivative.
Okay, thanks.
Okay, so yeah, believe it or not, this is just 2 pages of my 15 pages now lecture. So let us do a 5-minute break and then we come back if you want. So let us come back at 12:07. Okay. Okay.
Okay, see you.
Okay, let us start then. So a priori, there is no problem in using the above, for example, the bootstrap in particular procedure if you have a non-Gaussianities. However, what people tend to do is to for non-Gaussian cases, the convention or the typical procedure is to use confidence intervals instead. And this is what we are discussing now. So one has a series of observations again. So I start always with the same thing. So you have a series of observations, and then you have an assumed PDF for them. We want to estimate theta, okay? So, and then this will allow you to estimate theta by maximum likelihood estimate, and note that it will be a function of the true parameter, right? If the true parameter were different, then the estimator itself would be different. So, being this the case and being this function of data, then it is clear that this is a random variable. And if it is a random variable, I could write a distribution for this variable, depending on the true parameter, right? So if this is the case, then okay, let me just try to plot this distribution. Try to draw it, I don't know, something like this. For example, if this is the case, I can determine two values. And the values, let me call these values U alpha and nu beta. So here I have U alpha and nu beta. And these two values here will be such that you have that the probability for my estimator to be larger than U alpha, I mean, this is of course a function of theta, which is just it is equal to the integral between U alpha and infinite of this distribution. I'm just talking now in estimator space, okay? So now estimator is a random variable and I integrate over it. It is such that this probability is equal to alpha, meaning that this area here under this curve this is alpha. This area is equal to alpha. And analogously, the probability for the estimator to be smaller than nu b, also a function of theta, is given by the other tail. Okay, so and this is equal to beta. Okay, this area here is equal to beta. So then what would happen if you actually change? Because that was for a fixed, let me call this for a fixed value of theta, of the true parameter. But what if you change the value of theta? Then you would get another shape, another results, right? Another results for U alpha and for nu beta. So what we can say is that if this is a good estimator, I mean the maximum likelihood estimate, for example, is a good estimator of theta, then it should happen that you have the following behavior. As a function of theta, theta hat should increase as a function of theta. And then you will have some curve here, which will be the value of u alpha, and some curve here, which will be the value of nu beta. You see, no, I mean, if I would now consider a larger theta, then instead of being this, I will just be displaced and displaced, etc. So I will shift my distribution to the right, and consequently, the values of nu alpha, of u alpha, sorry, and nu beta will increase. And I can actually do that. I can actually do that for every value of theta. So I can, for every possible value of theta, I can have these two pairs of values of nu alpha and of u alpha and nu beta. Then what you do is to say, okay, so I have my real data, and this real data will allow me to compute the observed maximum likelihood estimate, I mean, corresponding to the real data. And this, let us suppose it is, I don't know, here. And if it is here, then I have this thing here. Let me just put this like that, just for drawing purposes. And this, which was called the confidence belt, will allow me, after observing the data and after estimating the value of theta from this observation, will allow me to compute an interval, which is a confidence interval, and this is going to be a confidence interval at, let's say, 1 minus alpha minus beta % confidence level. Okay, so alpha can be, I don't know, 0.5, 0.05, equal beta the same. So you will have something, some confidence interval at 90% confidence level. And this thing is so-called Niemann procedure. Okay. And these values of A and B, well, this is just, I mean, this is like inverting this function u alpha will be a function of the observed, right? So this -1 means inverting that function, okay? And this analogously for B. And this is the way to go. There is an equivalent way of expressing alpha and beta, I mean, these integrals, which is given by the following, and will be useful for what is presented next. This is 1 minus the cumulative distribution function of my estimator given A. And you see it is the same because alpha was, the cumulative distribution is something between -infinity and some value. So if I have now some value to infinity, it's like 1 minus the cumulative distribution, right? And the fact of being evaluated in the in this value corresponds exactly to A here. And if I do, I can write a similar expression for beta, which is CDF of observe given B. Okay, so these expressions are completely equivalent to these two expressions here. And what you do is just to take this and then let me call this one here. So you just solve this numerically for A and B, and that's it. So this is the procedure, of course. And of course, I mean, you can also have a one-sided or one-sided like a limit, you know. Now in this case would be a limit. Okay, so the interpretation of alpha, and this is important probably. So the interpretation of alpha, what it is just the fraction of times, no, that we would get a value of the estimator larger than the one actually observed. Just writing it, fraction of times that we would get a value for this larger than the one actually observed. Assuming that the value of the true parameter is A. And analogously for beta. The fraction of times that we will get a value smaller than the one actually observed, assuming that the true parameter is B. Okay, that is like the interpretation of these alphas and beta. Okay, so yeah, is there any question?
I have a question, Brian.
Yeah.
What happens? I mean, I guess that for this to be easily interpreted, usually theta shouldn't it be the median of the distribution, but since we are defining it as the maximum likelihood estimator, maybe you can have alpha that cannot be arbitrarily large. For example, it can only go up to 0.2 depending on the distribution or stuff like that. So how do you deal with this?
How do I deal with the
how do you choose alpha and beta?
Alpha and beta are chosen typically by what you want to have as a confidence level. So typically in physics, we work with 95% or 99, 95, 90% or 99 or whatever. And this will fix your values of alpha and beta. 95% confidence level, then you choose alpha and beta such that 1 minus alpha minus beta is 0.95.
Okay, I understand.
Okay, so let me just put an example here. An example from a Poisson, variable. So imagine having, so suppose having a single measurement. And this defines my observation. This is like the number of events of something. I have a question. What is the lower limit on lambda? Lambda is the Poisson parameter. Because I am assuming that this observable is distributed as a Poisson or follows a Poisson distribution for this confidence. I mean, you understand there is 100 here for this confidence level. So the way to go here is to say, okay, I am asked to have to report a lower limit. So I will use my alpha which is fixed by my requirement of the confidence level. And then I follow what is the definition of alpha, and was from from n ops, let's say, to infinity of this Poisson distribution, and evaluated at n low, right? So it is equivalent to this expression here. So I need to compute this and solve for lambda low. But computing this is easier if I convert this sum to the other one. I mean, this is from n equals 0 to n ops minus 1 of same thing, right? So it is because the sum of the probabilities is 1. So the area, I was telling the area of the corner, but the sum overall from 0 to infinity is 1. So I just converted this for computational purposes because it is easier to compute this other sum here. And then I just solve for alpha, okay? And if I ask about upper limit for a confidence level given by this, then I use beta from n0 to n ops of the Poisson times, given lambda up, let's say. So I solve for lambda up after fixing my beta. Okay, so let me just very briefly show you this. Yeah, so here, I have just an example, a numerical example of that. So this is a Poisson distribution, and I am assuming that n ops is 5, and I want to have, I don't know, lower limit at 95% and upper limit at 95%. So let me compute the upper limit first. So I go with beta, and then I just need to solve for a function which is that sum that I was telling you before minus beta, and this is going to be equal to 0 in order to solve for lambda, right? So I am just summing from 0 to n ops. I am just summing the values of the Poisson probabilities, like here, and then subtract with beta, and then use I don't know, a solver here. This BrenQ method is something related to the second method, where I give a function and I need to find the zeros of that function, but I need to make sure that I have endpoints giving me a change of sign between these two functions in order to make sure that this converges. Anyway, so by doing this and solving this function, I get at 95% confidence level, I get an upper limit on lambda equal to 10.5 if n ops was 5. And computing the lower limit is quite similar, right? Here I am just summing values of the Poisson distribution from 0 to n ops minus 1. And if you remember correctly, that expression was alpha was 1 minus some sum. So that means that this function, the zeros of that would be equal to 0 if that expression was correct. And I again solve for it and I get this like lower bound. So that is very simple. That was the way that I was doing it. I was just checking that reproducing this known result that for if you observe 0 events, what is the upper limit on lambda? And this is well known. This is just 3, a 95% confidence level. And by following the above procedure, this is what I get. So I get 3 essentially by computing an upper limit with beta. Okay. Any question? Okay. Then let me go back again to the notebook. To the iPad source. So what if now the estimator is Gaussian? So I'm just now referring to the case where estimator is Gaussian. This is a common situation, of course, because of the central limit theorem, okay? So I'm just saying that this distribution here is going to be a Gaussian distribution given by the mean of the true value, and I assume that the standard deviation is known. This is just an assumption, okay? Then, okay, I don't know, I mean, for the Gaussians, there are many properties. So you have the cumulative distribution, then would be, just to remind you that, sorry. And then these expressions here, this equation 1, I will express it in this case. Then 1 becomes like alpha equal to 1 minus the cumulative of the estimator given a mean equal to A, and beta will be the cumulative, where the estimator is B. However, note that I can express this as the following. So, and this is going to be the cumulative of a standard Gaussian, where the argument is now this one. And this will be the cumulative of a standard Gaussian, where the argument is the other one. So this is, I mean, this is a cumulative of a standard Gaussian, of a standard normal. I mean, this is the normal where you have 0 mean and 1 standard deviation, okay? This is a re-expression of that. So I solve now for A and B. And if I solve for A and B, so I am solving this equation for A and B, then I get that A is theta hat minus sigma times the inverse of the cumulative, which is nothing but the quantile, no? And B is equal to theta hat minus sigma times the inverse of the cumulative of beta, which, by the way, this second thing can be equivalently written as theta hat plus sigma of the inverse of the cumulative in 1 minus beta. Okay, it is because you are dealing with the standard Gaussians, you have this property. So these two expressions are the working expressions. And then what you do is to go to tables. So imagine you have central intervals. So if you have central intervals, then it means alpha equal beta equal 1/2. Sorry, gamma over 2. Then you have that these quantities are tabulated. No? So let me see if I have here. I should have here something like this. I don't know if this is more or less clear. Can you see this table? Yeah.
Yes.
Is it bigger? Okay. So here, either you fix the quantile and then you get the confidence level, or you want to fix the confidence level and you get the quantiles. Okay. So for example, I mean, I don't know, imagine that you want to go to typically people then just fix the quantile, the confidence level. So they go for 95% confidence level, then you get this for the central interval. In the case of central interval, and this is actually the case for a limit. So these tables are always very useful. But if you are going for a central interval, at 95% confidence level, then you will have this 1.96, and this 1.96 will tell you that that A is equal to theta hat minus sigma times this thing, or let me just put it at the end, 1.96 sigma, and B is, sorry, too fast, 96 sigma. According to these expressions here. Okay. Is there any questions so far? Okay, so let us go to another. So we have discussed about Niemann procedure, and this is like the most classical statistics that you can find. So let us discuss other typical uses of of techniques for computing confidence intervals. I am discussing now about confidence intervals using the likelihood. Okay, so it is quite used in practice because you may not have a Gaussian estimator or whatever. No? So you have your own likelihood and then you use it for that. And then yeah, so one first possibility is to use the idea of the graphical method So I am generalizing that idea and write the log likelihood in evaluated in theta plus minus n times theta hat. the sigma of theta hat. So I am here using a number of, I am using the quantile, okay? So this is the quantile. For making a generic expression, this is equal to log max, log of L max, minus n squared over 2. And this method, which holds exactly in the Gaussian case, it is also used in the case of non-Gaussian likelihood. So this is the use of that. Is that even if it is completely true for Gaussian, they also use it for non-Gaussian likelihood. And then, sorry, let me just put it here. This is true for Gaussian likelihood. But in practice, also used for non-Gaussian case. So this is going back to one of the questions we had in the first half, probably was Androniki, that. So what we want now is something of the following, plus D minus C, let's say. So you have in general asymmetric interval. We use the same expression. Right? And then we see, let us see in an example how this works. But this is going to be similar to what we already saw before. Any question? Okay. Wait. Stop share. Share. Let me see. It's probably this one. Okay. Okay, so here you're looking at some data, again generated by an exponential distribution, right? So I have here, I just have 50 data points. And then what I do is to determine, okay, this is just different ways of determining what is the optimum parameter. This is a generic, I use this because I wanted to test this function in Python that finds the minimum of whatever function, no matter how complicated it is, it should give an answer. Okay, of course, it depends on how complicated it is, it will be a better answer or not, but a good answer or not. But in general, this is a general purpose optimizer, let's say. But in this case, which is quite easy, the numerical value is quite similar to the true value, which is the mean of the data. Okay, so no matter, I mean, for this particular example, just take the mean here. And then I want to find the solution of this thing. Okay, and I find the solution. So I find the solution of this equation for the upper limit and for the lower limit. Okay, so I show you this before. So this is in general, the likelihood is in blue here with respect to as a function of tau. And then I want to extract what are these values here, these intersections here, this one and this one. Okay, so in order to do that, I just solve these functions. So I have, imagine that let us focus on this part, on the right part. And then I am solving this equation here. This is the log likelihood minus the maximum log likelihood plus 1/2. This should be 0. Okay, so I am shifting my argument by some x here, and I want to find the solution. So by how much I shift the optimum tau, or the maximum likelihood estimate, such that this function here is 0. And that gives me something around 1.2 or so, between 1.2 and 1.3. Okay, and then I do the same for the lower part. So I am shifting, like subtracting something from the optimum tau, and I want to find this the value of this x such that this is 0. Okay, and by doing this, I get the results, and the results are these two values that when I compute when I subtract from this value from tau, the optimum tau, and when I subtract optimum tau minus this, I obtain D and C. These two shifts to the right and to the left, and this is the result. Okay. So is there any question here? Okay. Anyway, so this is a method that allows you to get asymmetric uncertainties, even though you are abusing a bit of the method, because it is something that works for Gaussian, but people use it, and this is useful in many situations. Okay, so if there is no more question, we can proceed or can continue. Let me go back here. Sure. Then probably this is the last thing I will have time to discuss today. Do you hear me, by the way? Because sometimes I don't.
Yes, we can hear you.
Okay, very nice. Thanks. So the last thing I will discuss today is how to get confidence intervals using likelihood ratio. Why likelihood ratio? Because we have seen previously that the likelihood ratio is the test statistic given the highest power. So likelihood ratio seems to be like a good quantity to estimate my uncertainty here of the estimator. Okay. So now consider the following. Consider some data distributed according to a likelihood function. So I am omitting the dependence of the data now, but my function is depending on a number of parameters, m number of parameters. Okay. Some of these parameters are of interest. Let's say a subset of these parameters from 1 to k are of interest, whereas the rest are not. When I say are not of interest is I have a particular example where I have a likelihood where I have a signal and background as a parameter. I am interested in signal, but while I'm not interested in making a statement about the background, I do need the background in order to compute the likelihood, otherwise I cannot compute it. But I am interested in making a statement about only one of them. And then the idea is to see what do you do with this, that you need in any case in order to compute it. But these parameters here are called nuisance parameters, okay? Then the idea here is to create a test statistic for the parameters of interest. So we want to create a TS only for the parameters of interest. So how do you proceed? And by the way, then you will have the test statistic is going to be the likelihood ratio. So I will put the parameters of interest here, given the data. And this will be the log likelihood, so the likelihood ratio, and actually the -2 log likelihood ratio, where you have here the likelihood in θ1, etc., θk, and you have some estimation for the rest of parameters, which are the nuisance parameters. Divided by the optimum likelihood of all the parameters. So for every parameter, for any parameter here, this represents the maximum likelihood estimate somehow for the parameters of interest and for the parameters of the nuisance parameters. Okay, so this expression here, sorry. Can you give me 1 second, please? I need to do something. Sorry, I had an urgent call. So what I was saying is that this expression here, this expression in the numerator, this is called the profiled likelihood. And it is profiled over the nuisance parameters. So it is an expression which is actually only an expression, only a function of these parameters, because for all these parameters here, which are from k+1 to m, these guys here, they are a function of the parameters of interest. Is it clear, this part? So I haven't said yet how I am computing this numerator, But I'm just saying that at the end of the day, this is a reduced function where you only have these parameters of interest, because these other nuisance parameters, they are a function of these parameters of interest. Okay. So the way to go here is, so how do you do this profile likelihood? This is probably worth giving an example. So imagine again that you have S and B, and this is of interest, and this is nuisance. And then what you do, the procedure here is to do the following. So imagine that you have a grid of points. Okay. And this is a grid of points in S and B, let's say. So I have here S and B. So I evaluate the likelihood for every S. I evaluate the likelihood here, here, here. For this S here, I evaluate the likelihood here, 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 right? And for each of them, I take what is the maximum likelihood. So the B giving me the maximum likelihood. So let me just write it. For every value of S, I mean, this is just a plot, okay? For every value of S, I have my B hat of S equal to the R max over B of the likelihood which depends on S and B. And in that way, for every value of S, I do have a value of B. I have fixed my value of B. Or in general, for every value of the parameters of interest, I can have, for example, that this one is the one maximizing it, or this one, or I don't know. You understand, okay? And this is the way to obtain, at the end of the day, a numerator which is only a function of the parameters of interest. And this is the object called profile likelihood. Oops. Any question here?
I do have a question, Ryan.
Yeah.
I'm thinking, for instance, in this last example with signal and background, in the case of, I don't know, the signal depending on only on new physics parameters, and the background being totally independent of S. So how does this apply in that case?
The background doesn't depend on S in general, no?
Yeah, that's the thing. I mean, if I understood correctly, you said earlier that the nuisance parameters were function of the parameters of interest?
No, only after doing the profiling.
Okay.
Yeah, in general, they are independent parameters.
Okay.
You make the nuisance parameters being functions of the parameters of interest with this profiling procedure.
Okay.
That you are fixing the nuisance parameters to be those that maximize the likelihood for a given set of parameters of interest.
Okay. Now I see.
Yeah.
Thank you.
So one question.
Yes.
So is it correct to think of it like a projected likelihood in a surface?
Yes,
Of a
but well, a projection, yeah, but it is complicated because then you choose for every other dimension, the dimension that you collapse, you choose a different value.
Yes, right.
Yeah, but yeah, more, yeah, I can see what you're thinking.
Mm-hmm. Okay.
Okay, so all of this is useful because of the following. It's a very important theorem. No, okay, so what I'm saying is that even though you have reduced the number of parameters, you may have a large number of parameters of interest, right? So if you have these, then it may be difficult to, so this is difficult to get confidence intervals which are k-dimensional, right? For example, via bootstrapping or whatever, that becomes very, very costly. Okay. So then, in many situations, one can apply the following, and this is the theorem that is important, the Wilks theorem, which is heavily applied everywhere in physics. So here the Wilks theorem is the following. It is said that the likelihood ratio, this TS, right, given by, I mean, corresponding to the parameters of interest, this follows in the large sample limit a chi-square distribution with k degrees of freedom. Okay, so this is the theorem. So the only thing that you need to do then is to look at tables, right? So then it is useful because of that, because you can use the tables of chi-square, and I will show you an example now. I will take 5 minutes from you, where you see how to apply this. Okay. So let me just first see whether I have it. Any questions so far, apart from what I'm looking for this other thing? Okay, it doesn't seem to be a question. Let me try to see whether okay, I will show you then the example. It's going to take 5 minutes only. Stop share. Share screen. Share. Okay, so here I'm doing the following. I am generating some data. The data here is, don't worry, it's not Gaussian. I mean, it's not exponential now, it's another thing. So I am generating some data corresponding to 10 measurements of a Poisson observation, okay? How did I generate this data? It is some other, some detail that we can discuss. But for now on, just imagine that this data is given. So I have 10 observations following that I assume they follow a Poisson, okay? So then, okay, I have now, sorry, a Poisson, no, sorry, that, yes, that follow a Poisson. Then this Poisson variable follows like the expected value of the Poisson. I am assuming it is given by some, you remember yesterday when we were doing the shape analysis, that there were some fractions here times some signal and some fraction of background times some background here. So imagine that these fractions corresponding to the meaning, they are known, and I have these two parameters. And these two parameters, they are actually modeled in the following. So I am modeling my background as a normal distribution, as a Gaussian distribution, and I am doing the following. The total likelihood is going to be a product between the Poisson, and this is like the extended likelihood, if you remember, right? So I have the Poisson here, and then I have a distribution for the background, which is given by a normal distribution. Okay? So the total likelihood then is going to be a sum of these, the total log likelihood is going to be a sum of these two, the Poisson plus the log of the Gaussian for the background. Fine. So getting the optimum parameters here, I mean, means just two values, S and B. And then I will just use this function that I showed you before, and I have optimized my likelihood. This optimization of the likelihood with respect to all the parameters at the same time, S and B, or parameters of interest and nuisance parameters, this is like the denominator of my Wilks theorem. So I have computed in a way the global maximum, or in terms of the minus log likelihood is the global minimum. And I have obtained the parameters that for S and B that maximize this likelihood. And these parameters are more or less close to the true parameters, because I have started with 8 for the background and 2 for the signal. So I have 3.2 for the signal and 7.95 for the background. Okay, so what I'm doing now is trying to show you what is this, how does it look like. So I am plotting here in color code the value of the likelihood as a function of S and B. And this is what I'm plotting here. So in a way, I have this grid that I was talking to you before in order to do the procedure of profiling. So when I do the profiling, then I just scan for every function of S, for every value of S, sorry, I need to get what is the value of B maximizing my likelihood. And this is what I do here. So I profile over the likelihood. Don't worry, I will give you this notebook. I will send it to you. So don't get lost in the details. I'm just trying to follow what I'm just trying to say roughly here. So I am doing this procedure. I'm fixing S, and for a given S, I maximize my likelihood with respect to B. Okay, and this is what I get. For example, I have, if I put another value here for S, then I get another value of the profile likelihood. So after this procedure, I have gone from a total likelihood to a reduced likelihood, which is a profile one. And then how does it work? So you build your likelihood ratio. The likelihood ratio is given by the profile likelihood. I mean, since this is 2 times the log of the ratio, it means that you have the log of the numerator minus the log of the denominator. So we have all these ingredients, and this likelihood ratio is just a function of your parameters of interest, in this case, one parameter of interest. And I can plot the likelihood ratio as a function of the parameters of interest. In this case, as a function of S, and this is what I get in blue, right? And then I go to the table. Let me see if I have a table around here. Do you see it? Do you see this? Because I got an error here. I don't know if you have seen.
We can see it, yes.
Okay. So then you go to the table. In particular, I have taken this table from this very useful review on statistics and the PDG, the particle data group. So here you have this table corresponding to delta chi-square or 2 delta log likelihood. So this is what we need. And I say, okay, let me work, then I will have the confidence level fixed to be 95. Okay, and then how many degrees of freedom I have? I have 1 degree of freedom because I have one parameter, which is S. So I have only one parameter, so I look at this column here, and then I get that the delta chi-square should be 3.84 or so. So I draw a line here, 3.84, and then I get these intersections here, giving me the 2 values I need, which is 1.24 or so, and 5.9 or so. Okay. So sorry, I went very fast on that because I know we are over time. And in any case, I send you this this notebook. But is there any question on the overall idea of this?
I have a question. I understand this when you have only one parameter of interest, since it's a chi-square and so on, but if you have more than one, is it a multivariate chi-square distribution, or how is actually distributed? I mean, I didn't understand this too well.
No. If you have more than one, imagine that you have 2 parameters of interest. You still have that your test statistic is distributed as a chi-square. So no matter how many parameters of interest you have implemented, or you compute a test statistic which is one variable. This is a scalar. And this scalar, according to the Wilks theorem, follows a chi-square distribution. Okay. Is it answering your question or not quite?
Well, I can read the notebook and so on, and I think I will understand it better because I.
So imagine that I have here. Imagine that instead of having a signal here, I have 2 parameters of interest, right?
Yes.
This is your question here, no?
Yes.
So you have a profile likelihood of 2 parameters. Then you have a test statistics, which is the likelihood ratio, being a function of 2 parameters. Okay?
Yes, yes.
Now I can think of a 2-dimensional plot like this one, no? And then instead of being a parabola like this, it's going to be like an ellipsoid. It's going to be an ellipsoid, and I am away from the minimum until the point where I get, I don't know, 5.99. The delta chi-square, or the delta, or the 2 times log likelihood, should be 5.99 in this case, in this 2-dimensional case. And this defines what is my limit at 95% confidence level.
Okay, so you would intersect your curve by a plane or something like that.
Yeah.
Okay. Now I understand. Thank you very much.
Okay, great. Yeah, any other question? Sorry for this being over time. Okay, so if not, as anticipated, we didn't finish with this topic. We will finish confidence intervals tomorrow by talking about Feldman cousins, and which will be the last subtopic, let's say, before going to something else. But let us do Feldman cousins tomorrow, and then we continue. Okay.
Okay, thank you.
Thank you very much. See you.
Thank
you. Bye bye.
Thanks.